This lesson is going to be on horizontal projectile motion. So we're still on Unit 1A, and we've moved to Objective 2. There is a direct connection between this and what we did last class with kinematic equations. In fact, we're still going to use kinematic equations. We're just going to apply them to two dimensions, horizontal and vertical. So we can describe 2D motion quantitatively with graphs and equations. Today, we are going to cover solving problems with zero initial vertical velocity using kinematic equations. We're going to cover given a vector, solve for the components using trigonometry, and given a component of a vector, solve for the resultant magnitude using the Pythagorean theorem. That's what we're doing in this class today. And then next class, we'll deal with projectiles such as like a football being cooked towards goalposts or like something being thrown. So to begin with a warm-up that will help guide us today, we have a cannonball that's falling a height of 300 meters. So we have this height of 300 meters. It falls, so we also know some other variables. Identify the variables and solve, pause the video, and I will continue working on this. So you might notice that I am putting subscripts on these variables because we're going to start using two dimensions, and vertical and horizontal. And the easiest way to do that is identifying s of y or s of x. So y as showing like y-axis vertical motion, x is like horizontal motion, x-axis, things like that. Yeah. I'm also using negatives because we're gonna get in the habit of looking at projectiles are moving up and down. So it's just gonna be a good habit to use negative values when we're looking at objects that fall downward. All right, pause the video, and I'm gonna also pause the video and solve. All right, so I found that the equation was number 2, and I plugged these variables in. The one thing that I did want to show is the only thing I did is I made sure that all of my variables that are in that number 2 kinematics equations were vertical components, were s of y, u of y, a of y. Notice that there's no t of y, right? Because t is time. There's no vertical or horizontal components of time. And then I just plugged the values into the variables, and we got a time of 7.82 seconds. The next question is, what is the cannonball's final speed right as it hits the ground? Now recognize the answer is not 0. It's like right before it hits the ground because we're still in free fall. We're still in being affected by gravitational acceleration, not the ground's force. I have a u of y. I have an s of y. I have an a of y, and I have a t. But I need to find v. I think the easiest one is equation 1. I don't even need s of y. So v of y is equal to u of y plus a of y times t. So v of y is really just negative 9.8 times 7.82. So it's just however many seconds times g. So 7.82 seconds times g. And that's 76.7 meters per second. 7, that's a 7. Let me improve that. Meters per second. All right, we're going to take this this process of finding vertical velocity, vertical or time to fall, and we're going to apply it to a two-dimensional motion because really we're actually using the same work, just we're adding a horizontal component and just saying, oh, and it's also moving forward. So in this situation, let's identify some things that we do know that exist. A cannonball is shot off horizontally. Well, one thing I do know is my acceleration of my vertical, a of y, is equal to g, which is equal to negative 9.8 meters per second squared. And then we also know that my horizontal acceleration, actually we don't know this yet, our horizontal acceleration, unless there's air resistance slowing us down, this is going to be 0. That's huge, because that's saying that when I draw like a horizontal vector component such as this and call it like u of x, it's not going to change. So it's going to stay the same the whole time. Now, if there is air resistance, it might, slow down because it's hitting air in front of the ball. But if there's not, if we assume if no air resistance, then u of x is going to be equal to v of x, or a of x is 0. That's not the case, right, for y, and that's like the same work we've been doing in the past. In the beginning, it does not have a vertical velocity component. So that's nice. Right here, we have v of y is 0. And if we've already found out that when we know there's an original velocity of 0, such as in this case, I said v of y, sorry, this should be u of y, then it makes our problem much simpler. S equals ut plus 1 half at squared is not a quadratic anymore. So that's 0, but we do know it's increasing, right? And how much does it increase? Well, actually, let's give times, right? This is t equals 0. Let's say this is t equals 1. This is like, it's 2 seconds later, it's right there. 3 seconds later, it's right there. 4 seconds later, it's right there. And then 5 seconds later, it hits the ground. Well, similar to this problem, the second number 1, where we have a final speed, and we just noticed that the final speed is equal to the time times the vertical acceleration, so g. This is like 1g. This would be 2g. Actually, let's make it slightly smaller so I don't go too crazy. 2g. This would be 3g. This would be 4g. And this would be 5g. The velocity, right? So my v of y is equal to 5g, or however long the time it takes for it to hit the ground multiplied by 9.8 in the downward direction. So what we end up is seeing 2 separate problems. We see the orange problem, which is very similar to what we did in this warm-up, and this blue problem, which we can kind of extend and say, well, how far did it travel during that time period? But the key takeaway in this is that horizontal motion and vertical motion are independent of each other. Meaning that nothing that an object feels in a vertical motion affects what happens horizontally. The only thing that could affect both at the same time would be like air resistance, but the vertical variables of velocity and acceleration won't affect the horizontal variables of velocity, acceleration, so forth. So we're going to jump to an example because none of this is really new content. It's just new techniques of solving this content. So in this example, we have a cargo drop-off plane that is flying at an altitude of 2,000 meters high at a speed of 50 meters per second. It releases a box to drop off some supplies to a remote farm. How far does it need to be from the village horizontally before dropping it off? So in this example, there's our farm, there's our ship. It drops off some box, like here it is the box, and then it travels, and I just drew this diagram to kind of help us visualize what's happening. We also know that it's going to be dropped off at some angle, which we're going to use some vectors to find out. But we need to start identifying some variables in this. Also, diagramming is super important. So whenever you see a situation, imagine it, but also diagram it. It's going to make things a lot easier, and it's definitely a requirement. So I've separated my horizontal variables, and I want to identify what we have. So it's moving at a speed of 50 meters per second. That means this cargo box will also have a speed of 50 meters per second. That also means that down here, it also has a speed of 50 meters per second as well. So in my identify x variables, I have my horizontal initial velocity. I have my acceleration, which is 0. I have my final horizontal velocity of the same 50 meters per second. And I have my s of x, which is what we're trying to solve for. So we do not know that. We also don't know time, but since time doesn't have a horizontal or vertical component, I've put it in this little space in between horizontal and vertical variables. So we're going to eventually get to that, hopefully. Vertically, we need to identify the variables. Well, we know that originally u of x is 0, and that's kind of, in terms of the motion of it, that's all we know. So we know u of x is equal to 0 meters per second. We also, I'm sorry, u of y. And we also know that the s of y is the height, and that's equal to negative 2,000 meters. And I'm keeping to the negatives just to try to enforce that. And we also know our acceleration in the y direction is negative 9.8 meters per second squared. We don't know our final velocity, and we don't know the time. But we've seen this problem before. We have u, s, and a. Where have we seen this before? Back to number 1, u, s, and a. And we were able to solve for time. We were able to solve for final velocity. So let's do that. We're going to use our s of y is equal to u of y plus, u of yt plus 1/2 a t squared. I'm going to pause this video and kind of work through this. I'm going to show my work so you just don't see me working. All right, so using the work we have, we end up with a time of 20.2 seconds. And I also said that time is like our connection in between here. So I would say t equals 20.2 seconds. And I would even say, let's move that all the way up to here. And that's t equals 20.2 seconds. And I could solve for my final velocity if I would like to in my vertical direction. So let's go ahead and do that. And v of y is equal to, well, this is the easy one, right? Because u of y is 0. So we just know it's 0 plus negative 9.8 times 20.2. And that's 198. Again, I'm going to identify that I like to round to like 3 sig figs pretty consistently. There are rules that we're going to learn, but IB tends to kind of forget about them until the very end, or there's only like one mark that you have to do it. So just 3-4 sig figs is a pretty common rule to stand by. Okay, so I've got my final vertical velocity. I'm pretty good on this right side, so I want to go to my left side, and I want to solve for my s of x. So I have my u of x, I have my a of x, I have my v of x, and I have my t. So I can go up to here and say, hey, look, what equations do I want to have? And there's a few values I can use. I need to find s, so I need to find an equation that has s in it. So it's either 2, 3, and 4. Now I just solved for time, and one thing you'd find is if you use 4, you're going to end up canceling everything out because a is 0 and v is equal to u. So let's use equation 3 because I don't think we've used equation 3 yet. This is s is equal to u plus v over 2 times t. And this is going to be a silly one because this is 50 plus 50 divided by 2 times t, which is just, s of x. So that's s of x is equal to, 50 plus 50 divided by 2, that's just 50. So this is just telling you that s is equal to ut. Similarly, we could have used the second equation where there's plus 1/2 at squared, but that a would have been removed because a is 0, so it would have canceled out, and it would have just been s is equal to ut. So that's the good news. In x direction is pretty straightforward. And my time, I didn't plug in my time. Why didn't I plug in my time? Is 20.2. That's 1,010 meters. So this distance away from right here is 1,010 meters. And we have solved the problem. We've identified how far it needs to be, about 1 kilometer away, and then it drops the box and it'll land in the farm. Example number 2 starts identifying angles. So what angle does the box hit the ground? And I pulled out a image from your data booklet. This is in your data booklet, so you are always given how to solve for components, the horizontal component and the vertical component. It doesn't include the Pythagorean theorem, so you just need to know that if we're using this, like AH squared plus AY squared is equal to A squared, or, like a squared plus b squared equals c squared. That's just something you're going to have to memorize. So what angle does the box hit the ground? And all I also say is what speed is it traveling? And I'm using speed. I'm not using velocity because speed is the final, the magnitude of the speed going in this direction. So we have a horizontal speed and we also have a vertical speed. And so we have vector components that we need to use. So let's just imagine, let's redraw the box here. And let's give it a horizontal speed of 50 and a vertical speed, what do we end up finding at? 198, so something like 4 times the size of that vector. One thing I also am identifying here, I'm not sure if this was really hit home when we did vectors, but when drawing the diagrams with vectors, you need to make them proportional. This is 198 meters per second, and that's about 4 times the size of my blue arrow because that's about 50. So you're going to really, really, really need to do that. And then we're going to need to find our final velocity, which is like, it would be like this. Because there's your horizontal component and there's your vertical component. And we're going to need to find the angle and the magnitude. So to find the angle, let's just start with the first one. We can use a few ways, right? But the most common one is seeing this as a right triangle and seeing that, let's look for like how much it's below the horizontal. So let's look for that theta. Well, if that's the theta we're looking at, then I know that my right triangle is this. My hypotenuse, I do not know yet because that's the magnitude of my speed, but I do know that this side is also 198. And so I have my opposite and I have my adjacent according to that angle. So actually, let's erase this because this doesn't need to be here. And actually, technically, this is the right triangle, the one I drew, but those sides are equal, the 50s. So I'm going to find my tangent. Tangent theta is equal to opposite over adjacent. And so that's equal to 198 over 50. So I'm going to have to find my inverse tangent of 198 over 50. If what I just did right there feels uncomfortable for you, I highly, highly suggest you practicing through the vectors worksheet. Make sure that you are on angles and not radians. And I would find that my theta is 75.8 degrees, and I need to write below the horizontal, because my horizontal is this right here, and my angle is below that. Okay, that's the angle that it hits the ground at. What speed is it traveling? Well, I need to use Pythagorean theorem for this because I have both sides and I need to find my hypotenuse. So I'm going to say 50 squared plus 198 squared is equal to my final velocity. I'm just saying v. There's no x, there's no y squared. And so 50 squared plus 198 squared is 204 meters per second. So it's traveling pretty darn fast and at a pretty big angle, so you're going to need a sturdy box for that to land. So that's the end of this practice. Continue with the practice problem. But let's make sure that we've finished this. Let's see. So we've solved problems with 0 initial vertical velocity, given a vector, solved for components using trigonometry. Well, we used tangents. That could use some improvement. So that's the extra practice with vectors. And given a component of a vector, solve for the resultant magnitude using the Pythagorean theorem. We did that. So that's the end of this video. Begin the practice problem.